Okay, thank you, everyone. I'm Niall Murphy. I work in a particularly obscure subdivision of Willy Wonka's chocolate factory known as Google Limited, or something like that. My colleague is Todd Underwood, also employed there.
For now.
For that. But there's still time, because
There's
quite a while. The picture there you see is a rubber duck. Well, actually, it's probably not made 100% from rubber, which was built by, I think, a Dutch artist called Florentine Hofmann. The original scale model was about 1 inch wide, and that's about 32 meters, like 100 feet wide or thereabouts. We would like to think that the same engineering principles which informed the construction of this rubber duck enable us to think about how we manage distributed systems and how SRE might apply at various different scales. Although we aren't 100% sure because we haven't finished making the bathtub yet.
But to be clear, Niall, that one is both far away, but it is large?
Yeah, exactly.
Sorry, Father Ted.
Anyway, so let me hit next. Yeah, so agenda, we're going to go through some introductions, talk a little bit about SRE and what we know. We, in this case, is Google, obviously informed by the SRE book, which we did earlier this year. We'll talk about SRE at large scales and at small scales, introduce the Murphy-Wood diagram of fabulousness, which was not my choice of name. Talk about why Randall Munro might be wrong with a very large number of caveats, which Todd will introduce, and then have some final thoughts. Okay. So I call on Todd.
Hi, I'm Todd. I'm an SRE. That was good. See? I told you they would do it. What do you need to know? I've been doing this computing thing for 20-ish years or so. We don't like to talk in exact years because we're getting older now. Like many of you, I spent some time in ISPs, AS2901, if you're looking it up. I came from a systems background and a networking background as well, so interested in the intersection of those things. In 2006, I gave a pretty well-received talk called IPv6 is dead and everyone knows it. And I think the important thing that you should take from this is I'm prescient. Like, you should listen to me because I can predict the future, right? So it's really important that you note that. I was here in 2013 and I said some stuff. Mostly it made people angry and then they invited me back. And so I think there's a serious quality control issue at USENIX, and I'm going to put it in my feedback and you may wish to as well. Tell us about yourself, Niall.
So I'd like to point out that at this stage, my main function in this talk is to behave as straight man to Todd's plan. So just so we got that down.
Adult supervision.
Adult supervision. You remember what happened the last time, Todd. So I've been in the industry for about 20 years as well. I come from a systems and networking background. You can read about that at www.internethistory.ie, which is kind of the story of my early career and what happened to the internet in Ireland. 11 years ago, I was in Amazon. I think I still have the scars somewhere. 10 years ago, I joined Google. And today, I manage the ads reliability engineering team at Google, which keeps the infrastructure processing umpty $1 billion up. So no pressure. Most of you who know me will know me because of the picture on the next slide, which we'll talk about in a moment. Something else I wanted to say is that I felt that Todd's picture, corporate picture, was just a bit too official to really represent what he's about. So I put this in at the last moment.
It was fantastic. So my children were insufficiently impressed by my lack of Halloween attire and insisted that I dress as a fairy. And so this is their attempt. Thank you for that. This is quite good.
No worries. So how many of you have read the SRE book as a matter of interest?
How many of you have it on a desk that you occasionally visit and fully intend to read most of it real soon now? Yep, that's the majority.
Cool. That means most of what we have to say is entirely new to the audience.
Exactly. Good.
Okay, so we're going to go through a bunch of the properties of SRE as, that we understand as SRE as outlined in the book. Hopefully this will be new to many of you. I think to begin with the simplest possible diagram, maybe that's not a simple diagram, simplest possible diagram, about the contrast between SRE and SWE, which in this context stands for software engineering. So back in the day when a full stack meant a full stack from hardware all the way up, I would say that SRE and SWE have a similar total breadth of scope, except SRE is downshifted towards infrastructure. And software engineering or product development software engineering is kind of upshifted. So one way to think of this is that these professions have similar amounts of knowledge which are required to be effective in them, but the areas of focus are different. Okay, so you almost never find SRE writing user-facing JavaScript, like UI relevant stuff. You would find us, stop shuddering, you would find us rolling it back or
There you go.
or perhaps eliminating it entirely, but we generally don't write that. Similarly, you almost never find a classical web product software engineer writing disk drivers. Like that's a couple layers above their concern. It's a bit more complicated than that, but that's kind of a useful simplifying diagram. A small update, I guess. Even though we have a similar span of concern, obviously most of the issues that we tend to encounter on a probabilistic basis would, in the SRE case, tend to be somewhere above POSIX or in the infrastructure layer, and most of the time that the software engineering profession spends would be in the business logic layer or infrastructure supporting the general idea of software construction. As service owners as well, SRE tends to spend a lot of time on automation, which is one of the key things that we do. And essentially, we want to make our jobs go away or our lives more efficient. So, to expand on that diagram and talk about a few key points of SRE, one simplifying but useful story that we can tell is that SRE is a new way of doing IT and engineering operations. So when we first started doing SRE in Google, which is about 2003 or thereabouts, the traditional model of product development and systems administration with a hard separation at the machine boundary or production boundary environment still broadly applied. It certainly still applies in very many places today, but some of the rest of the world has moved on. I think one way to think about this is that IT work is some kind of two-dimensional space, okay? And you can slice IT work up in various different ways. For example, hypothetical example, let's suppose that we sliced IT work up such that there was a team responsible for pressing the letter T on your keyboard every time you needed that. So you could type LS or DF, and that's all fine, but if you needed to cat something, you would have to get somebody from this team to come over and press it on your keyboard.
And this is both a good metaphor and quite sensible division of concerns. T's can be quite dangerous.
So there are arbitrary slices that can be taken of this work. I think one of the things about SRE is that the engineering component of it tends to be with respect to products and services and infrastructure. In other words, that slice of IT work, which in the traditional model is wholly owned by the product folks, is jointly owned in the new world. And it turns out that there's a lot of reasons for doing that, and that this breaks some of the harmful incentive structures that would normally or previously have applied in traditional companies. I think one interesting effect that you see here is this phrase, cloud is your SRE. That, of course, doesn't necessarily offset responsibility to be intelligent about how you construct your applications, but it is an illustration of how a particular slice of work has now been taken and is being done by cloud providers in many cases. Of course, some additional work has moved in to take that place, take the place of that work, including arbitrage between different cloud providers and cloud-independent layers and so on. A couple of other points is that we've found, for us anyway, that it's been better to have folks who explicitly have reliability in mind and are charged with that as a function of their job role, rather than having it smeared across a bunch of people, none of whom maybe precisely care about it as their first concern. That turns out to be a pretty powerful thing. And again, we have a separate organization for doing that. So product software engineering and site reliability engineering are different. I think the main thing to leave this slide with is the idea that, as is key to DevOps philosophy, breaking that feedback loop between how your thing actually works when it's out there in production and the software engineering organization. If that feedback loop is broken, that's really pathological, it's really bad. It separates you from knowledge that you'd actually want if you're going to construct the best possible product. And one response to that is the role of SRE, one of whose jobs is to connect the wisdom of production to the actual engineering of the product.
Just quickly before we move on, I do want to point out, so like everyone else, we went to Flickr, we set the right license, we picked a bunch of pictures, but Niall is a fantastic photographer, and the vast majority of these pictures are from him, not only because they're excellent, but because he agreed to royalty-free license them to make the lawyers happy. So, thank you, Niall. Nice picture.
He didn't tell me he was going to say that, so I just want to
There
put
will
that
be
out
more
there.
surprises.
Yes. So, I guess I should start out with that.
So, what would you say you do here? I am so pleased. Where's
Well.
Thor? Like, I was like, I'm like, that slide. Has anybody ever hired the Bobs? Because neither of them has had a stellar acting career since that movie, and I feel like it wouldn't be that expensive to just get them into an office and bring people to that office one at a time and have them ask them, what would you, like, does that sounds like a reasonable expense, doesn't? I'm sorry, go on. What would you say you do here, Niall?
Adult supervision, Todd.
Yes.
So, SRE has formal responsibilities on, well, in my employer, basically on a per-service basis. So, obviously improving availability. It's in the name. Well, it's almost in the name. A synonym is in the name. Capacity planning, which is obviously deeply connected to availability. If you don't have capacity, you can't serve, therefore no availability. Incident response, again, deeply connected to availability. Latency, which is often, well, I guess in the infinite case, latency is unavailability. But in the finite case, it's often a very important user-facing property, characteristic of software. The performance and efficiency of that software in production. Change management. Architectural review and consultation. It's a very important function because, as is well known in the software industry, the sooner that you make a change in the software lifecycle, the less that it costs, the easier it is to do, so on and so forth. We've found that consulting earlier with product teams means that we get much better outcomes as a result. It's much cheaper, better for everyone, really. Automation, particularly critical at large scales, but also critical at smaller scales, as we'll see, and monitoring. So it's important also to note that we're not just deployed when there's an on-call requirement, although incident response is one of our formal functions. We are there as part of a business goal. The entire infrastructure that surrounds SRE swings into place, and we do a lot of good things for the product when we're attached to a product. But even at Google, we're not attached to all of the products. Like on average, there isn't an SRE team for a product because there's a long tail. And so something that we didn't emphasize too much in the book, which in retrospect is probably a mistake, is that software teams at Google are DevOps by default, in the sense that if there ain't anyone else to do the on-call incident response, performance, blah, 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 like, it's you, it's the product team. Okay. So, talking a bit about, we'll talk a little bit in this section about the fact that there are a bunch of good reasons for SRE to be used in companies which are now large, and you might look at Google and other companies and say, oh, it's being large that actually helps SRE or makes SRE work for them. But in fact, Google was much, much smaller when SRE started. I think in 2004 had something like 800 employees, so presumably it was less in 2003. And while talking about SRE today often is associated with talking about large companies, there's in fact a good deal of things you can do which are scale invariant. Or to put it another way, a lot of people think we have infinite money, resources, and chocolate, and that's why SRE works, but it's not true.
Which part's not? We don't have infinite chocolate? Which is the...
I know I behave as if we have infinite chocolate, but we don't actually have infinite chocolate.
Damn it. A redundant array of infinite chocolate.
Don't know if any of you garden. Do any of you garden? Yep. So turns out that
I like the...
You like the... Yeah, maybe a little bit.
I try to garden. It doesn't always work out. That was just... I feel that way.
So it turns out that certain kinds of soil support certain kinds of flowers, and it can be difficult to grow certain things in the wrong soil. Conversely, suitable flowers grow from suitable ground. Or another way to put this is that Google was probably particularly appropriate ground for the practice of SRE, for SRE to emerge, for a number of reasons. I mean, culture and technology and practices inside the company and all of these things kind of contribute towards like people behaving in different ways, of course. But I guess in 2003 or thereabouts, we had folks, software engineers, working on the search engine. I think there was just the search engine then, maybe a bit more. And those people cared about the system working. Right? Some subset of them cared about the system working. They cared about like getting a new index built correctly and out to production and so on. And they had exactly the same skill sets as kind of all of the other engineers in the company, the people writing the products. So they were in a position to talk similarly, use similar vocabulary towards similar ends. The subset of people called production team also had fairly urgent requirements around scaling, possibly, obviously, and scaling rapidly furthermore, which drove a lot, but it didn't drive everything about the practices that emerged at that stage. And indeed, production team, which cared about this stuff and did SRE type work at that stage, did it before there was an SRE name for it. So that kind of behavior emerged earlier. Another thing which probably contributed to the emergence of SRE at Google was the fact that if you consider some parallel universe where Google Prime in this parallel universe is writing, we'll say, Win32 API desktop software, which it's burning onto CDs and posting out to people and so on. The focus on reliability that comes from web applications which are centralized and which you have positions of leverage to do things with does not apply in the disconnected postal CD desktop application model. And the fact that we had view of the stack because we used open source software in the way that we did meant that we were in a position to fix things wherever they needed to be fixed, and we didn't have to call out to third parties much to do that kind of thing. Okay. So that's why it emerged. It continues to be successful in Google, and there's a bunch of reasons for that as well. So we have a very supportive environment for this happening. SRE is well known in the company and has a good reputation. We have Clúfil air cover as the picture of the Aer Lingus regional airplane flying to Cork over some apartment building might lead you to believe, or maybe not. We had systems that benefited from SRE coverage quickly enough so that the feedback loop could be understood as operating well. And we also had what I'll call a single source tree. Of course, there are various, I think Android and Chrome and so on are not in the main repository necessarily. There's a paper by Rachel Potvin on research.google.com about this. But we have a single source tree, which means that if there is a problem, an SRE on call or in the middle of a project or whatever can find that place in the source code where the problem is or where that needs to be extended, or to do facts on the ground investigation in a way unimpeded by any other gatekeeper. Of course, it continues to be successful, but it's also costly. Hiring is very hard, generally hard everywhere. Sometimes we make mistakes.
It's true. It's true.
We pay the cost for running a separate organization. Part of the reason for that is so the voice of reliability can never be silenced. Like if we're in a meeting with product development or whatever, there's the separate reporting chain makes it a bit harder to override that concern. And we also have a somewhat fragmented existence because we have to serve the two masters of production and software engineering and so on and so forth. Now, so you might look at all of that and say, well, SRE clearly succeeded at Google because we had infinite chocolate and great software skills. To the extent that they're statistically correlated, I don't know. Risk-tolerant management, all of those things. But surely SRE is doomed at a place that doesn't have these things. So I guess it's important in that context to note that not all of these mostly large companies who are doing SRE or experimenting with SRE do it in the same way. For example, we heard from Craig earlier this week about how LinkedIn does embedded SREs with product development, and Facebook does something similar, which we don't typically do in the Google context. It seems clear that whatever is dooming SRE to inapplicability, it's not necessarily a separate org structure. Maybe it's not necessarily other things as well. In fact, we argue that SRE is much more generally applicable than that. So the key point is that we claim that SRE works at a large scale, but in fact, there are many practices, approaches, which are scale invariant, which also mean you can do SRE successfully at smaller scales, non-Google scales. So SRE can work in small environments. With the key summarizing principle for it being that a small amount of work now saves you time later, okay? Or in other words, a stitch in time saves 9. Now I always had a problem with that saying because I'm like, 9 what? Like 9 scalar what? Something? But it turns out that this phrase, apparently coined in mid-1700s or thereabouts, means that if something's about to break, a stitch now will save you having to do 9 stitches later on when it's totally rended apart and you need to stitch it back together again.
And I do have to add, as a not very good knitter, I will say that if you drop a stitch, it doesn't fall 9 rows and then hang out. It just keeps going until you pick it up, right? So, like if you, anyway, I think there's challenges here. We'll come back to it. This is an important point. We're going to dig into this stitch thing.
Thanks, Todd.
I did not knit this jumper, by the way.
So, SRE in the small. That photograph, by the way, is from a wonderful place called Mini Europe in Belgium. I don't know if anyone's ever been there. But it's got representations of important national landmarks for each member of Europe, and I suspect they're going to have to do away with the tiny TARDIS, which is the UK, shortly enough. Anyway, I guess I should crack on with story time. So talking about a few examples of what I mean when I say a bit of work now helps you avoid a lot of work in the future. So I used to work in the .ie domain registry. This is like 20-something years ago, or possibly a bit later than that. And I was handing off my work to a new guy called James Raftery. Shout out to James if you ever watch this. And I noticed while we were huddled over some keyboard that he had a zone file open and he had loads of names with the same A record in this zone file. And I was like, what? Why are you doing that? You have SMTP, A, whatever address. You have POP, A, same address, etc. Like, why are you doing that? Because it's just going to the same computer. This was 20-something years ago. Please forgive me. And it turns out, he said, well, I'm doing that because if the clients put mail.domainregistry.ie into their Pegasus mail, as it was at the time, then we can change that A record or the implementation of that service from underneath them without having to change the actual name, which will be less work. So it's a tiny bit of work now to save more work later. Blew my mind. So,
I do want to point out that if Niall's going to show embarrassing pictures of me, we'll need to show embarrassing pictures of Niall. So this is roughly coincident. It took me quite a bit of effort. Thank you to Nick Hilliard for providing this. I think he conspired with Niall's wife as well. So for those of you who know Nick, good guy. This is Niall at roughly this time of history. So you can see there's some sort of historicity to it. In this time of year that we are entering into end-of-year festivities, you will note the lovely jumper that he has on. I think this is appropriate for an ugly Christmas sweater party. Thank you, Niall. Please continue. Sorry for interrupting. Go on. Let's have another story.
Thanks, Todd.
Cheers.
It is good to note that I'm approximately as smug-looking now as I was then, which is useful. So story time 2. In a previous employer who shall remain nameless, there was a data generation process. This process ran regularly out of cron, read some stuff, produced some output, read some stuff, computed, produced some output. And this got copied to production by some relatively stable and reliable process. So the data generation process made some assumptions about the availability of the underlying storage system, didn't check return codes properly, particularly of opened and read, and was otherwise essentially primed to produce nonsense as soon as something significant went wrong. However, one engineer had the foresight to have a callback in that code, which at the end of the ostensible end of the production of the output would be called. And this engineer thought that the simplest possible placeholder that they could have in this code was to iterate over the in-memory data structure and just check the size wasn't equal to 0. In this particular case, because there was a null build error and it couldn't read any data, the size of the in-memory data structure was indeed 0, and the problem was caught there. Now, it was caught there rather than systems-level checks, because they also might have failed due to the intermittent unavailability of the underlying storage system as well. Or, to quote another proverb, prevention better than a cure. So in general, these stories show or illustrate our general point, which is judicious work ahead of time is useful and prudent. And now I call on Todd to talk about this in more detail.
So I think what we're going to try to do is pivot from the particular to the general. So you've heard some stories. Story time is lovely. Any of you who read it's called news, North American news, like one of the things if you're not used to North American news is like the first paragraph always has a human being. It's like this, like these are like talking about some macroeconomic factor, and it's always Bob Jennings of Nebraska says that, and you're like, but I thought this was about labor force participation. Who's Bob? Like, and he's just a person, but they do this because all of us are compelled by stories. There was an excellent presentation about stories So you've heard stories, and now you should be compelled. But we're going to try to argue for 7. Everybody's compelled, right? Like, now you're listening. You're listening. You're like, yeah, I heard a story. I loved it. What we're going to try to do is present 7 principles. The first section, I'll just present the principles and say, like, I think these are approaches or techniques or suggestions for a way in which at any size is the claim. So down to the single person operation, deploying a single application stack or a set of related application stacks on somebody else's cloud, all the way up to, you know, in Google scale or Amazon scale or Facebook scale, very big organization. Great. Right, so we'll present these 7 principles, and then we will walk through. So as I'm presenting them, you're going to be thinking, I think that's kind of crap, and I think he's wrong, which is fine. So we may think we are wrong as well. We will go through what we think are sensible objections to each, and some will survive and some will not. And by the end of the presentation, you'll have a tiny list of actionable things that you can do at any scale, and you'll have to promise us that you will no longer wander around the world saying SRE is only great for Google. Is everyone on? Are you ready for this ride? This is what we're going to do. Okay, good. So the first of these, load tests. How many of you have load tests? There's a very small number of hands. So how many of you are asleep right now? Okay, good. That's more hands. So, and there was no intersection between the sleeping and the load test. That's interesting. So look, like the general idea of a load test is you throw something at the thing that does the thing, and you find out just when it breaks, right? That's fantastic. If your application is consisting of several stages, you can throw independent things at each of the stages. An end-to-end load test is like by far optimal, but also really hard to construct. You need a lot of spare resources to stand it up. But some kind of load test, even if it is a particular targeted load test at sub-representations of the individual components, will give you information about just how much capacity you have. Ideally, you would want to use live traffic for this because it is very, very difficult to synthetically represent the kinds of problems that you... So people who use your service, anyone who does something for someone else in here, which I assume is all of us, they're a pain, right? Like, if they would go away, this would be easier. So, like, it is very difficult when we come up with the requests to send to our systems or the data to process through our systems, we come up with sensible things because that's what it's supposed to do, the sensible thing that you built it for. Unfortunately, many of our users do not do those sensible things. So, super important to try to use live traffic if you can. Everyone clear on what I mean by load tests? Rocking. Next. Export your application state to some sort of monitoring and logging system. So by this, let's be clear, like by this I don't mean, you know, find out how much RAM the process running your application is using. That is a good thing to graph, that is a good thing to store, that is important for certain kinds of troubleshooting. What I mean is, whatever thing your application does, export information about that from within the application. There's a bunch of monitoring frameworks that make this possible. I think the one that I've seen, and it's possibly like an architectural bias of mine that makes it easiest, is Prometheus. But you have a client library, you have some variables, you just say like, that one, that's a good variable. I would like to periodically export that. You need to store the state for that away from the application so that you are able to detect particular failures in the underlying infrastructure by looking at what happened in the application. Particularly useful are things that regard information about a long-running process that is underway, right? All of us have had this state of like, is it stuck or is it slow, right? And you want to wait, but you don't want to wait forever. And so having some information to say like, this process takes 2.5 hours. We are 46% of the way through. We are 47, we are 48. You're like, good, okay, fine, keep going, that's fine, right? That is the kind of thing that is very, very difficult to tell from outside of the application. Everyone clear on exporting application state and why it is completely rad? Completely rad? Good, I saw thumbs up for completely rad. My children tell me no one says rad, and it makes me think they're bad at logic, because right in front of them, right before that, I just said rad. Maybe they're bad at human languages. Monitor now. So even if the things you know how to monitor, the things that you're able to easily monitor, the things that you can think of to monitor, you're pretty sure aren't the right things. You should monitor something as quickly as you can anyway. Any monitoring of almost any kind is better than no monitoring. And any more monitoring is better than the monitoring you have now. So it is a truism among those of us who have worked on systems and love those systems that we are always deeply dissatisfied and frustrated and embarrassed by our monitoring. This is just true. Every single one of you who's ever monitored anything, if I got you in private and we sat down and like, how's your monitoring? You'd be like, it's terrible. It just doesn't detect the right stuff, and it gives me false positives, and it's not correlated with the kinds of failures that I want it to be correlated with. I have this really good idea, and I just haven't had time. That's fine, but I have heard people use that as an excuse for just not working on it. They're like, it's going to be terrible. Screw it. Not going to monitor anything. I'm not just going to go with what I got. That's not the right approach. Even if you are not happy with the monitoring that you are going to have, even if you are not happy with the ideas, the correlation, you should monitor stuff. Everybody clear on this? Monitoring grand, yes? Lovely. Okay, some of this is going to start getting slightly more controversial. So, dependency tracking. By dependency tracking, I'm talking about two things. People who are depending upon your code application service and code application services your thing is depending upon. So both ways. At a minimum, the recommendation here is that you are aware of and can periodically audit the people who depend upon you and the people you depend upon. Depending can be a library that you build into your application. It can mean a service that you send and receive RPCs from. It can mean an authentication system that you rely on being up. At a minimum, we recommend that you are able to track these things. Now, the next step up from that, which is not that high a step up, is that you are able to prevent or at least alert on new dependencies, either dependencies on your service or dependencies that you have. I will mention a caveat in the sort of humble pie thing. This is not a thing we do well at Google right now. There are systems that we are working on, and there are actually people here from Google who work on some of those systems to track dependencies, but I do not want to pretend that the complete version of this that would automatically prevent anyone from calling your service unless you whitelist them and have a reasonable system for enumerating all your dependencies. I don't want to present that that is easy, but some simple version of this is not terribly difficult and presents some pretty significant advantages. So, clear on this idea? Yes? You went to sleep on dependencies? Really? Okay, this one. Many people are not happy with this one, but we're going to talk it through and try to consider the alternatives. So, shard early, shard often. This is a representation of, this is a discussion about data storage, right? So, if you expect your data to grow and you would like to be able to scale easily, then dividing your data among multiple shards earlier is easier. Right? You will get the code that expects to have multiple shards. You can reshard later so that instead of 2 you have 8, or instead of 8 you have 32 shards. But you are able to do that quite easily once you have the infrastructure to do that. When you write code that assumes that all of the data is in one place, that code is very brittle and it is very difficult to ever shard in the future. So this is a change which is quite cheap to do early, which is quite expensive to do later. Now, Tom Limoncello is sitting over here and he's like, it's like, whatever, you don't need no shard. Is it still true that you all do not shard and it's been fine? Bygones.
High five.
Stack Overflow doesn't shard its database, but it shards its logs and search.
Okay. So for those who couldn't hear that, it's a discussion. It's a fairly famous discussion. It's a really interesting case that's the counterpoint of this. The answer that Tom gave was that Stack Overflow doesn't shard its database, but it does shard its log collection and analysis system. So, and that could be, anyway, we're going to discuss pros and cons of this, but everybody is clear on, is everyone clear on what we mean by sharding? Is this like a super, everybody's got it or nobody's got it? How many people went back to sleep?
Yeah.
We're not going to get through this if you keep falling asleep. Yes?
Do you only mean data, though? Because I would argue this is true for all your bits.
So the question is, do we only mean data or do you mean all your bits? I think here specifically we're talking about data storage and structured data access as a suggestion. So
anything for which you might find yourself writing application-specific code later on. Yep.
Excellent. Okay. Next one. Distributed applications require proper distributed consensus. I know that people don't like Paxos. This is the grottos at Paxos, the actual Greek island, right? So I know that people read Leslie Lamport's paper, or more appropriately, most of us tried to read it several times. We got lost in the middle of that third page and went back and then gave up and then read Raft, and that made a little bit more sense, and we couldn't remember it, but at least we know where the paper is, right? So I know that this seems like algorithmic magic. It's not algorithmic magic because lots of people you know actually understand it, and there are lots of implementations of this. The mistake that many people make regarding distributed consensus is they think, I don't really need that because I'm just small and I'm not that distributed, so I will just identify my services excuse me, and distribute my computation in a semi-static way. Basically, I'll push files around, I'll put it all in that database over there, it'll be fine. And when I distribute work to like a bunch of tasks, well, not a bunch, I don't have a bunch, like 10 or 12. I mean, it'll be 20 later or 500 later, but right now it's, so people do that. And then at some point later on, you realize that you really don't have any guarantees about which one of these tasks has which bit of data that they're working on, or which one of these databases is the currently live master. So without distributed consensus algorithms that are well understood and trusted, you really, really don't know what the heck is going on. Where's Seth here? Seth was talking about console. It has Raft at the core for exactly that reason, right? So this, beyond a certain size, and that size is smaller than you think, you got to use real distributed consensus. Questions? Rad. Okay, this one is not obvious to people. So this is a representation. Niall hates people. I hate people too, but Niall is smarter than I am. So Niall took 50 euros and paid to go a kilometer up in the air in a balloon to get away from people. So
cheap future isolation.
That is cheap, right? So there's an example of 50 euros, kilometer up, no other humans nearby except for the 8 people in the balloon. I'm not sure. You should have just spent like 400 euros and gotten them all out of there. Let me explain this core idea. You are doing something, you receive requests or receive data into your system. Put an identifier on it that says something about what that is, and pass that identifier to the next stages of whatever it is you do. So in a web application, data comes in from customer who is like in this class of customers, or customer in this geography. Slap a label on that request and pass it along. You don't need to do anything with it now. Later on, someone will say, we need to really answer requests from customers in Japan within 20 milliseconds, but from customers in Germany within 200 milliseconds, because this is something important about the way those people are using which parts of our application. You'll say, yeah, sure, no problem. And you will simply write a little thing that says, if Japan, jump to the head of the line, go to the fast server. If Germany, they'll wait. Right? Similarly, the most common example of this is separating batch or throughput traffic from live traffic. Right? Some of your systems are called by other systems, and some of your systems are called by people. And your other systems can wait. Like, so you have a system that looks up, what items of chocolate you have in your apparently not infinite inventory. We're going to get back to that. So you have a system and it looks it up. Now, sometimes the system is used by your stock crew who are trying to order more chocolate to continue to provide the illusion of an endless supply of chocolate. So you want the stocking crew that works in the snack kitchen to have very fast access to the inventory information about all of the chocolate. Now, you also have a system that does a report at the end of the day. Who cares, right? It does the queries and links. So put a little label. This is batch. This is from this application. This is an end user coming on from this web farm, and plumb it all the way through your infrastructure. Easy to do. And so now we enter into the section of little known fact. I didn't learn this until I moved to New Mexico. In most parts of the US, I believe it's true that the correct response to if you disagree with it, is yeah-ha. Is it people, right? Yeah-ha. In New Mexico and also in many parts of Hawaii, it's yes, huh, which just sounds interesting. Anymore, a little bit more of linguistic geography.
Very good.
We're going to walk through these, and we're going to present some arguments and have some verdicts. Niall.
So I guess the most general objection to the mechanisms approaches we've seen so far are this is not simple. Like, this is effort we're going to have to spend now. This is unnecessary complexity. We have to keep it as simple as possible, but no simpler, obviously. Or to put it another way, Yagni, you ain't going to need it. So only do it when you need it. Or designing unnecessarily ahead of what you need. So partially this can be answered by a thresholding question, but also by our general recommendation, which is that actually much of the infrastructure required to do some of these things is smaller than you think and can swing into place relatively easily. So load tests. Load tests are unrepresentative toil. They're a lot of work to produce. You have to keep them updated, track how live traffic changes, and maintain them. You have the maintenance burden, etc. So unless your applications are really very simple, this doesn't actually buy you anything. And they can also lead to outages themselves if you happen to replay the traffic back at the wrong place. So they don't work. They don't necessarily help you, and they can, in fact, harm you. So no way they're useful.
All right, come on. Like, this is a truism. You will have a load test. Either you will run it or your customers will run it, but you will have a load test of your system. The thing I like about my load tests is that I can stop them when they turn into a problem. And there is one system I work on where we have not been able to create a load test that is equal to the equivalent customer load. So that's a problem. And even systematic, even sort of individual systems, unrepresentative load tests can give you valuable information about the capacity of subcomponents. So I do agree that load tests are a fair amount of work, and importantly, I think in our industry, there are not great automated tools for them, but I still think worth the time, worth the effort, even for small applications. Niall, what is the verdict?
Verdict is, well, there's a bit of a trade-off here. They are awesome, do not forget that, but they are expensive and add toil, so maybe not initially.
Sad. I swear, some of these ideas are going to survive. So load tests didn't make the cut.
So, exporting application state, obviously this adds time to implementation. I mean, it takes a long while to type printf or cat that into a log. I am trying to say this with a straight face, ladies and gentlemen. Probably the most difficult point, actually, is that the instrumentation, judgment about where the instrumentation is placed is actually fairly tricky. Like, you can get it wrong by having too much instrumentation. You could instrument every if statement. That'd be rad, as they say.
See? People do say it.
It also reduces performance because I guess that if you instrument every if statement, you have a lot of disk I/O. And exposes security problems because almost certainly somebody will write something that printf %s's some class of user ID or password, because none of us have ever typed a password into a user name field at any point ever, and so have privacy vulnerabilities.
So debugging without application state is guesswork. And we've all been there, and it is frustrating. And the fact that we have this technique available is fantastic. Many failure modes are super specific to the application, what it is doing, what is the work that it is doing, what are the error conditions. There are some application environments that are poorly instrumented in one of my teams. One of those environments runs along and says, I am using 4 gigabytes of RAM. Now I am using 18 gigabytes of RAM. Now I am using 7 gigabytes of RAM. And you say, like, hey, dude, to the application. I don't know. In this case, the application is a dude. You say, hey, dude, what's up? Like, and it's like, I don't know. I had some stuff to do, and now I have less of it. Like, what are you going to do with that, right? So exporting the application state. Libraries make client-side instrumentation really quite palatable. The Prometheus client libraries are really easy to implement. You just select some things, and they get exported for you. And printf, not super challenging. What is the verdict? Yeah, see,
Clear
there we
win.
go.
Ding.
Excellent.
So bad monitoring, bad operations. So it's obviously worse to have metrics that lead you astray and lead you down the garden path than it is to have no metrics at all, because at least you can use your native brain power to figure out what's going on. And we've all come across the moment when the monitoring is so slow, or the monitoring server has crashed, or the dashboard won't render, et cetera, et cetera. So it's just easier to cat the log files that you're not printfing to.
A small collection of well-understood metrics is massively better than none. I think the argument that you will be so bad at selecting what to monitor that you will deceive all of your future selves is a spurious argument. The recommendation here is not to monitor as poorly as you can with the dumbest ideas you can think of. The recommendation is to not allow your lack of perfection to impede you from monitoring the things you believe are useful about your application. And my contention is you are not as stupid as you think you are, and you are definitely not as stupid as apparently Niall thinks future you thinks you are. So, lots of easy ways to do this. Monitoring pays consistent, huge, and enduring benefits. And in the end, you will do it, so you might as well get going right now.
Our survey said, ding, monitoring is non-negotiable. Please do it early and often. Fine. So it's turtles all the way down. So let's get real, ladies and gentlemen. It is never possible to entirely enumerate all of your dependencies. We all know this. There's just too much at the software stack, never mind the RPC layer. And most of those dependencies aren't actually problematic in any actionable way, like pending a RPM upgrade or something like that. And the frameworks for dependency logging and auditing and blocking can themselves be the cause of outages or other problems, particularly if they require dependency injection or similar magic infrastructure. And all of that infrastructure does cost something and reduces the performance and simplicity of the overall application. So,
first of all, I really don't understand the picture. I'm not good with pictures, but apparently it's a failed dependency. It's a kitty and a bear. They're trying to eat a thing they can't eat. Reasonable efforts on dependencies give you reasonable trade-offs. I think that the logical fallacy in Niall's objection here is to assume that you get no benefit unless you have correctly enumerated all of your dependencies. I acknowledge you cannot enumerate all of your dependencies in an easy-to-use fashion. However, I think the more you enumerate, the more future problems you can easily address. So the objective is not to secure your infrastructure in this case. That is a different problem. The objective here is simply to harden it against future you, who, again, is not as bright as you wish they were. So prudent dependency testing, recommended.
Not always worth it. Maybe later.
It is a lot of work.
So database sharding. Where are you coming from when you say this, Todd? It is unnecessary. It is unreliable. If Stack Overflow can do it, so can anyone.
It's true.
Your complexity rises. Your reliability is down. Maybe you picked the wrong shard. Maybe you got the parameters to the new call the wrong way round, and you're invoking reading a shard string where you should be reading a shard integer or something. Maybe you're writing in Python. Maybe you have a slow shard. Maybe that lagging shard is going to cost you performance. And probably the largest, most significant question from an engineering point of view, what do you shard on? Not all of your data will hash in the right way or block in the right way or arrive in easy chunks to materially slice up.
So I think two things. Precious servers are dangerous. All of us have had the precious server that if it goes down, everything goes down, and all the services or a set of tightly interconnected services are all on that server. Distributing your data is a way to avoid your database being the precious server. future growth is difficult to predict. And many of us will look at this and say, like, my application's this big, and Moore's law goes like this, and I think it's just always going to be under the curve. It's very difficult to know that, and the future cost of sharding is quite, quite high. I will acknowledge that it is difficult to know on what key to shard. So you could shard on, chocolate type, or you could shard on, snack kitchen, or you could shard on, employee chocolate consumption, employee ID. But you have to pick something. But at the same point, you know your application, and you have a rough sense of the kinds of queries you can do. Not that expensive or difficult to do this early on. Pays big dividends. Come on.
Our survey said, sharding is cool. Sharding be cool, but it's hard to get right. So do plan this carefully. So, Paxos. Oh, just use a configuration system. It's not that hard. They're unnecessary overhead. They're complex. Like, I lectured on Paxos, and I still don't quite understand it. Distributed consensus is really hard to debug. It's also the slowest file system ever in the history of the world. So,
there is really compelling historical evidence. Those who do not implement Paxos or Raft or something like it are doomed to reinvent it with horrible corner cases badly, repeatedly. This is really not optional when you are doing distributed computation. If you are positive that you're only going to ever have one of those things and know which one is the thing, that's great. But the minute you start distributing, especially distributing across failure domains, it is not optional to have a proper distributed consensus algorithm. Every other kind of I'll just push the file to this has some really horrible failure modes, which includes everybody writing to different places, and now you have like live data that contradicts itself in multiple places.
Laura Nolan has a good article on this in the SRE book if you're curious about more, which you should be, because distributed consensus is not optional.
Excellent.
Now, identifiers. We don't need no stinking identifiers. They are an extra parameter to parse, keep track of, store, retransmit, shard, hash, I don't know. Anyway, complexity leads to errors, leave it out. And also the function signature complexity, which increases the refactoring cost and the risk. Uh-oh. Yay.
So if the objection to not using identifiers is you're unwilling to add items to your function signatures or to your RPCs, I find it unlikely that you will be able to do any other software engineering, since at some point, calling some code involves the thing that you are calling with. So unless your application is done and baked and never going to be touched again, at some point you'll add some things to your function calls, to the signatures, or to the RPCs. And they might as well include identifiers. So not the most compelling argument. I think that the debugging value of identifiers, especially in a distributed environment, which we didn't even talk about before because the argument had previously been, you can do different resource allocation performance, different application-centric behavior if you have these things. But it also incredibly aids debugging if you have these plumbed through your system because you can find out what happens to individual requests. So, come on. Thank you.
It is worth it.
Thank you.
It pays off. Tom Killelea, ex of Amazon, has a good article on microservices and some of the trade-offs there, particularly what happens when you externalize your call stack, which is essentially what happens in the case of microservices. So,
all right, so I'll just briefly point this out. Many of the arguments that Niall was generous enough to make, even when he didn't believe them, against these ideas amount to a collective objection against a microservices stack. People have been talking about this, and there were actually a few presentations at this conference sort of either referring to or making parts of this argument. Microservices stacks, distributed computation where you send RPCs to different portions of it, they add complexity. And the arguments in favor of microservices actually started off as mostly arguments against monolithic binaries. The arguments against monolithic binaries were, they're really hard to build. It's really hard for lots of software engineers to work together on them. It's hard to enforce call boundaries. It's hard to enforce separation of concerns. We've all heard these arguments. And I think the argument is that many people are making now is that small teams don't need microservices. Small teams are able to coordinate and communicate inside of a big binary. It is possible to test and repeatedly deploy big binaries. Multiple UIs can be served by individual large binaries that serve different flavors of the UI to different people or do different kinds of computation. So monoliths, big software monoliths, can have strict separation of concerns. This is the argument.
So in fact, microservices we think are useful. From a software engineering point of view, they actually enforce clear boundaries and API usage. You're not actually able to have the call stack go over to the other computer unless that's authorized, unless that's been explicitly constructed in that way. And many things on a systems level which require easy isolation of some subcomponent, scaling and tuning, deploying, provisioning, are much easier in a microservices environment than they are when you're rolling out the newest version of the monolithic binary, that patch level of which might have picked up other features or problems that caused that to be required to be rolled back. So some things software-y are, of course, harder. Just generally the complexity of managing the interactions of these microservices on the layer above their own individual operation, of course. They're also particularly useful in a web context because of how we do distributed applications. And they're also useful in enterprise applications where you have many of these individual instances of small teams that Todd is talking about. Of course, if you ain't ever going to need it, that's totally fine, you can avoid it. But it's really hard to be explicitly positive about that from very early on. So, okay. So, just a couple points on automation. Automation is at the oily mechanical heart of what we do in SRE.
It's such a gross image. Like, why do we have an oily mechanical heart?
Well, here you go, Todd. This is what you got to do.
All right, so Randall Munroe is wrong. Wait, so I am actually required, I think, to read the entire disclaimer. Look, he's not really wrong. I mean, he's a cartoonist and a satirist. He's more clever, more productive, a better human being than either Niall or I, and we all know that. And even in this XKCD, there's a deep truth. But how the heck are we going to be able to get your attention if we come in and say, well, we have an interesting sort of very small modification to a point that he made in a comic? No, sorry. Some of the contents may have settled during transit, void where prohibited, limited in supply, Puerto Rico, Guam, and the US Virgin Islands, offer not valid for employees of XKCD or their families. Sorry, please.
So as I was saying, this comic points out the universal truth that we've all experienced, which is that we have a problem. We say, I know, I'll write some software to solve that problem. What happens then is that the writing of the code, the debugging, the thinking about the problem domain, implementation, and maintenance then take up the time that we would have saved by just doing the original task ourselves in the first place. So a deep truth, but perhaps some difficulties as well. And
XKCD is wrong again! No, seriously, you're here again. Sorry, here's the disclaimer. I'm really sorry that we weren't clear. XKCD is awesome. This is a clever and useful chart with nice utility and a very, very clear point to make. In fact, it's not only right, but it's got some deep truth hidden in some very simple arithmetic. We're just trying to say that there might be more to it than just this. Do you know what I mean? We like and respect Randall Munroe, and the world is a better place for his genius. Thank you.
That was class. So this comic is an attempt to point out, to illustrate how complicated and how time-consuming it is to actually automate, or, to put it another way, how long is it permitted to work on automating a routine task before it becomes inefficient, i.e. before you spend so much time that you actually should just have done it yourself. So this graphic can be a little hard to parse. I think the x-axis is obviously the thing along the top, which is how often you do this task that you're hoping to automate. That might be a constant, or at least it doesn't seem plausible that it would change between 50 times a day and weekly that often. And the y-axis is how much less time you want this thing to take after you have done your automation work. So, for example, if you say, I do this thing X every day, and you want to make it take half an hour less, you can spend up to 5 weeks on it before you're overspending. So it turns out that this graphic, which suggests some pretty profound limits on what it makes sense to automate, is wrong. And it's wrong in the sense that there are benefits beyond that pure mathematical comparison, which we'll talk about. I guess in a startup where every second is precious and it's often difficult to think beyond what's going to happen today, or even the next few hours, never mind on the quarterly boundary, like that's just incredible long-term thinking when you're burning through angel funding at a rate of knots. Another way to think of it is that the toil that you're buried in now is actually a function of decisions you made earlier. And so to that extent, it might sound difficult, maybe mechanical, but setting aside time explicitly on every day in order to do something to make the future better turns out to be to yield benefits. So let's look at the Monroe Doctrine. Monroe Doctrines and their issues. So Monroe Doctrine 1319 has some problems. I guess, obviously, software development in the first place doesn't necessarily take as much time as outlined there. The time to do the original task that you lost is actually okay if the software is doing the original task. But more importantly, the original task might expand. So you did a particular routine task, which suggests very much that it repeats. Today you've 10 customers, in a quarter you've 100 customers, and maybe some kind of progression like that changes the task. So getting software to do it might be necessary anyway, and it's probably cheaper to do it when the number of customers is smaller. And when you've shipped something that works, that's actually a platform that you can go on to expand or use in other things rather than just a task you've completed, maybe a little bit like the difference between rent and mortgage. The Monroe Doctrine 1205 has the other problems that, firstly, amortizing the cost, as that previous graphic does, of software construction over 5 years turns out to be like not the right number. Most software, as we talk about in the SRE book, persists for much longer than it took to write it, and 6 to 8 years is probably a bit more of an accurate figure. The value of what you get after you write the software is also not fully accounted for. But probably the major objection is that the table assumes that you're the only beneficiary, that it only saves time for you. But most people don't work in isolation. They're in a team, and that routine task is often not limited to one person. It's done by a bunch of people. So people are in a position to gain, other people are in a position to gain from your time expended in writing that software. Or, to illustrate it more graphically, having copied that table into spreadsheets, the top spreadsheet, the cells are colored green where, economically speaking, it makes sense, and also from a realism point of view, like to spend 4 minutes on writing a piece of software, like it's probably not going to be able to do that much. So the cells are colored green where it's above a day in seconds. And you're spending a day to write software to save other things. So that span of control there suggested by the green cells is where it's relevant to write software to save time, just to solve it for yourself. But if you solve it for somebody else, if there's just one other person in your team who's going to benefit from what you write, then the value is doubled. It immediately expands the possibility space of what you can spend your time on to automate so that your team and the company and so on will benefit. Other dimensions of benefit exist. But here's where we get to the Murphy-Wood diagram of fabulousness.
You really hate that name.
I do, very much so. So this is, in honor of an earlier talk, a phase transition diagram, which suggests that, in fact, if what you're going to do, so the choice is between chores or code. Do the chores, and the thing is done at the end of it, but you've got nothing to show for it. You do the code, and the thing is done at the end of it. It takes longer, but you have something to show for it. In this diagram, attempts to answer the question, should I put code or should I put chores here? And the answer is, only if the data is static or small, and there's a small number of people who will benefit from this, should you do chores. The answer in every other case is almost certainly code. Maybe not immediately, but sooner or later. So, I guess some final thoughts. It is difficult to explain what we do in SRE, not just to the rest of the industry, although we do that, but also to ourselves. For example, our job title, okay, Site Reliability Engineering. A couple of months ago, I gave a talk with Chris Jones, one of the other co-authors of the book, about SLAs and SLOs and so on, I think at SRECon Santa Clara. And we started talking about site reliability engineering to a bunch of people who weren't familiar with the role. And I found that when we were saying the job title, that the word site was becoming more and more, it felt more and more inappropriate to me. We don't manage just sites. We manage a variety of things, ranging from payments processing to network devices to services generally. So maybe site isn't the right word in what we do. Maybe we should just be reliability engineers. But then I went, ladies and gentlemen, I confess that I went and I bought some books on reliability engineering in order to figure out what this field had to say to us. And I read the tables of contents. And I read some other things as well, but not that much. But I looked through the table of contents, and these books are about the manufacturing tolerances, the tendency of certain electronic components to fail. Obviously, that has some overlap with what we're doing, not a huge amount. It's about sophisticated statistics about mechanical component dependence and so on. There is a lot about the profession of non-site reliability engineering, which is so conditional on the physics that it has very little to say to us about our mind stuff, the software that we work with every day. So I started thinking then that actually it wasn't site that was inappropriate in our name, but maybe it's reliability engineering which is wrong. But then I came around to thinking that what we really are is, yes, site reliability engineers, but we're actually stitch-in-time engineers. Todd.
So just to remind you, we promised, did we promise? We alleged, we claimed that we were going to give you some actionable things that work at any scale. Niall kvetched and he argued and he complained and he made a couple good points I'm forced to acknowledge. But this is what survives, and this is what survives that we claim is actionable and in rough order. So you are responsible for some infrastructure. You wrote it yourself, somebody else wrote it. First thing you should do is monitor what you can right now. Second thing you should do, export application state, whatever application state you think might be relevant, as early as possible. You're done with those two things. Things are going pretty well. Add some identifiers to your call stacks, either to function signatures or RPCs. And then as you start growing a little bit, add proper distributed consensus to your application, either by using some software that someone else wrote or deploying infrastructure yourself. In this order, these are the ones that clearly survive, provide benefit to people responsible for production infrastructure at almost any scale. So, thank you.
Thank you.
No throwing of popcorn or tomatoes, but we will take questions if anybody has them. I was kidding about the tomatoes. It's fine to throw tomatoes. Sorry. David.
Thank you very much for the talk. So I have a question. Can you say a little bit about what you think about exporting application state in the situation where the application consists of fragmented situations or highly ephemeral components, or in the sort of the degenerative case where you're talking about functions as a service at Lambda, et cetera, or even in the slightly more common case where you've got pipelines?
Yeah, so actually there's a really good chapter on pipelines in the book, and Dan Dennison has been doing a bunch of work. He works with me in Pittsburgh. So if you have like a distributed pipeline and you have lots of workers, you do not want each worker telling you a whole lot of things about exactly which thing it's working on. But there is in that application some controller or some workflow management system that is aware of, I have 111,000 tasks, 53 of which are owned by these people right now. So it is not going to be the case that down to the finest level of granularity, you always want to export everything every application is doing. But yeah, in the case of a distributed computation, anything that is orchestrating or managing that distributed computation, that's where you would want to deploy that.
And is that true in your opinion, for, say, Lambda sort of like situations?
So one common approach is if you have a lot of ephemeral functions or jobs or whatever, which might spring into being and vanish back, that they post their state to some well-known stable source, which can in turn be monitored. So there's some kind of proxy, long-lived proxy to capture that state.
Thank you.
Should we go over here?
Sure. Thanks for the talk. You very carefully use the word identifiers.
Yes.
Do you have an opinion on whether those identifiers should be versioned or broken down and structured in some way?
I think so. So I think that's advanced thinking, and it's clever thinking, and it's good. But you can get a bunch of the value by having free-form strings. Like, do your best. It's application specific, so you would have to think like, what might I want to separate in the future? And I give a bunch of examples, and any application you have might have very different examples. But versioning them is certainly a clever idea, and it's good, and it would future-proof some of the things you're doing. But I don't think it's required, and I think you can get a bunch of benefit from taking a more naive approach.
Thank you.
Cheers. Over here, and then we'll come back.
So you responded to some of the specific objections that people typically bring up, and that makes sense because you're current Googlers. But as an ex-Googler, I'd like to make an observation, which is that most frequently I've heard these objections voiced, and most strenuously, by other ex-Googlers who were not SREs. And I mean, I just think I don't know what that means. I think it may be that they, at Google, they found that dealing with SREs was difficult. I don't know. I don't actually know why. But
it is unquestionably true that dealing with me is difficult, and I am an SRE. Therefore, QED, SREs are terrible. I'm sorry, so the point is that application developers or people in engineering who are not SREs find these sorts of requirements really tedious or difficult or daunting in some way.
Right, and they'd be the ones that would argue with me most vociferously that we're not Google, we don't need that scale. We're not Google, we don't need consensus. We're not Google, we don't need sharding. And just, I don't know what it means. I'm just throwing that out.
Interesting point. Do you have anything clever to say?
Yeah, the only thing I would say is that you don't have to be Google to insert an extra parameter into a function which never gets called, and then the growth of your business is such that it turns out you never need it, and you can refactor it out 6 months later. Like the idea is to do a small amount of work now to save larger work later, and the converse argument is let's do larger work later. No.
Okay.
Alice.
Yes.
Hi. I just wanted to clarify something from my own understanding. When you talk about a sharded database, would you include something like Cassandra there, or would that be a step beyond a sharded solution?
Sure. So yeah, no. Using Cassandra is just you outsourced your sharding to someone else, right? So you you bought into a client library and a sharded implementation. Yeah, there's a more traditional version of people deploying relational databases, or even people deploying unsharded, like NoSQL key value stores. That's a disaster.
Sure. See, like I'm moving from a sharded MySQL implementation to Cassandra, and I'm just wondering. Okay.
Yep. And that's a thing, and it's a thing where, like, similarly, I assume you have to eat some implementation cost of doing that, but in exchange, you get to scale out the Cassandra later on your own without significant difficulty.
Yeah, it's been really nice. I was just wondering if that was like, you're encouraging people to get to like the sharded MySQL step, or if it's also like, no, Cassandra is also good. Like that's what you mean by sharding.
I would say Cassandra is also good.
All right. Thank you.
For many people. Yes, here.
So, thanks for a marvelous talk.
It's marvelous. It wasn't
it
fabulous, but it was marvelous.
Marvelous.
It was marvelous, yeah.
Okay, excellent.
We've never actually met, but I'm Mark Burgess. I wrote the introduction to
Mark.
your marvelous book.
Thank you.
Okay. So thank you for that, and congratulations on the publication. I wonder if you clarify a point about the Paxos. So a lot of distributed applications are not homogeneous in the information they need. Do we need to distribute information on a need-to-know basis, or does everybody need to know absolutely everything? And the reason I ask is that the cost of distribution is very high. And it's clearly a scaling issue. So perhaps you'd comment on to what extent or what strategies would we use to distribute information consistently over the, pardon me, the scope where it's needed.
So this could be quite a long conversation. But I guess I'll say that in the systems that I have direct experience with in my employer and outside, distributed consensus is used to arrive at some token which specifies where in the overall history of a thing you are. And there you can decouple that agreement on what the history of the thing is from where you store the thing or how that's manipulated. So on that basis, no, you don't. Not everyone needs to know everything, and that, in fact, information hiding and a bunch of other good design principles would lead us to that opinion anyway.
I think I'm allowed to say this. The people who do production engineering on Google's distributed consensus system, so you know how to make Canadians angry, you just have to say ice hockey, implying that there might be some other valid kind of hockey, right? Right? See, I'm like, there's a Kanokastanian in the back shaking her fist at me. It's fantastic, right? So the thing to make the folks that work on Google's distributed consensus system angry is to call it a file system. Now, it has a file system API, and you can enumerate the things in it and make it look like a file system, but you're absolutely right. The performance is catastrophically terrible because consensus is expensive. So you do have to be thoughtful about who needs to know what, and as Niall says, I think you pick identifiers or tokens or magical numbers where you need to. What's that?
Index?
Index is good. Yes, a labeled index is fine as well. Yeah.
Cool. Thank you,
Cool.
gents.
Thank you, Mark.
Cheers. Two more questions. Oh, and there's two. Look at that. There's that one and that one. Go ahead.
So we don't make software. We provide a service, and that service is turning your tax dollars into conference papers and ultimately giving people a piece of parchment at the end that says that they did stuff like that. Are there any lessons in all of this for people who are not basically in the web application industry, who don't make apps, who just are trying to run an infrastructure that supports something else that is not that sort of thing?
Yeah, one of the things that's tough for us is we use application examples that we're familiar with. But yeah, I think you run some computing infrastructure that's used by some people. You can monitor that computing infrastructure. You get requests from users that come in on a port, network requests for service. Files show up and need to be processed. Data needs to be backed up. At many levels, the concerns there are not fundamentally different. If you don't know where your backups are and I don't know where my backups are, we have exactly the same kind of problems with our bosses, right? So this is a thing, and I think I'm still employed. So yeah, I think monitoring is a thing that that you already do and should do more of. I think these techniques absolutely do apply. See, last time it timed out all the time. Here it was right at the end.
Thank you.
I was just wondering about the distributed consensus because in my experience, that's something that sort of has to be put into the whole system. It's not the responsibility. Is it something that, you know, there's these SWEs and the SREs, and they all have to work together to create a system that's has distributed consensus in it. It's not something that I just sort of want to see how that is introduced at Google.
So I think I'd say two things. The first thing is that it depends on the application or the system in question. So obviously, if you have some database which is related to some business function or other, you just can't immediately Paxosify it.
That's the neologism of the talk right there. Paxosify.
You have to figure out what the right design is there. However, if consensus is implemented on the infrastructure layer, such as in our employer with a file system type API, you can take advantage of that in various ways without having to get everyone to buy into that, because opendir and read and write calls will work on some kind of file level.
Yeah. Excellent. All right, well, we'll be up to take further questions. Thank you so much.
Thank you very much.